Assalamualaikum everyone. Welcome back to Sir K Loves Physics and Chemistry tutorials for high school students. In this episode, we take a closer look at the perfectly elastic collision in one linear dimension. Two problems are analyzed that will require you to apply the laws of momentum and energy conservation. So join me till the end of this video. Watch and learn. Question number 1. Object B is at rest when object A collides with it. The collision is one-dimensional and elastic. After the collision, object B has half the velocity that object A had before the collision. Question letter A. If the velocity of object A before the collision was 6.0 meters per second to the right, what is its velocity after the collision? Letter B. Which object has the greater mass? And letter C. How much greater? As illustrated in the figure, object A is moving at a constant velocity v sub 1 equal to positive 6.0 meters per second and is about to hit a stationary object B. Just after the perfectly elastic collision, object B has half the velocity that object A had before the collision. Hence, b sub 2 prime, which is the velocity of object B just after the collision, is equal to positive 3.0 meters per second. And our target variables are b sub 1 prime, or the velocity of object A just after the collision, ma, which is the mass of object A, and mb, which is the mass of object B. We are also asked which between the two objects has the greater mass. Since this is a perfectly elastic collision, we can apply the equation for the coefficient of restitution, denoted here by small letter e. All right? And in a perfectly elastic collision, the value of the coefficient of restitution, small letter e, is equal to 1. All right? So this equation was derived from the principle of the conservation of kinetic energy. All right? So the value of the coefficient of restitution equal to 1 is equated to the relative velocities of the two objects before and after collision. All right? The quantity b sub 1 prime minus b sub 2 prime is the relative velocities of the two objects just after collision, while the quantity in the denominator b sub 2 minus b sub 1 is the relative velocity of the two objects before the collision, right? And we also consider this collision to be or the system to be an isolated system. In other words, the interaction of objects A and B are not in any way affected by external forces such as friction. So the law of conservation of linear momentum applies in this situation. All right? The law of conservation of momentum, as you may all know, states that the total momentum of the system before and after collisions are equal. And in this problem, all right, we write the equation for the conservation of linear momentum in terms of their masses and velocities. That is, ma times v1, which is the momentum of object A before the collision, plus mb times v2, that's the momentum of object B before the collision. So their sum is what we call the total momentum of the system before the collision. And that is equal to MAB1 prime, which represents the momentum of object A just after the collision, while MB times B sub 2 prime is the momentum of object B just after the collision. So their sum is what we call the total momentum of the system just after the collision. Moving on to our computations, we first find the velocity of object A just after the collision, denoted here by b sub 1 prime. Alright? So, this working formula for b sub 1 prime is of course derived from the equation for the coefficient of restitution in a perfectly elastic collision. Alright, so b sub 1 prime is equal to b sub 2 minus b sub 1 plus b sub 2 prime. Substituting the given data, we have b sub 1 prime equal to 0 minus 6.0 meters per second plus 3.0 meters per second. Or that is equal to b sub 1 prime equal to negative 3.0 meters per second. Alright, so this is the velocity of object A just after the collision. In short, object A moves with a speed of 3.0 meters per second and it is moving to the left. Alright, and to find the relationship between the two masses ma and mb, we make use of this equation for the conservation of linear momentum. Alright, which, as we said earlier, alright, the total momentum of the system before the collision must be equal to the total momentum of the system after the collision. So when we plug in the given data into this formula, we have ma, which is the mass of object A, times its velocity before the collision, 6.0 meters per second, plus mb, which is the mass of object B, times its velocity before the collision, which is, of course, equal to 0. And on the right side of the equation, we have mass of object A, ma, multiplied by its computed velocity just after the collision. Alright, the one we just calculated in letter A, p1 prime, which is negative 3.0 meters per second, plus mass of object B times the velocity of object B just after the collision, which is 3.0 meters per second. Alright, and this can be simplified to ma times 9.0 meters per second, alright, equal to mb times 3.0 meters per second, which results to, alright, the mass of object B, alright, being equal to 3.0 times the mass of object A. Alright, so this is the relationship between the two masses, which means that object B has the greater mass compared to object A. All right. Object B, in fact, is or has a mass 3 times the mass of object A. For our last question, number 2, blocks A with a mass of 2.00 kilogram and block B with a mass of 10.00 kilogram, okay, mass or object B is to the right of object A and it's moving on a frictionless horizontal surface. Initially, block B is moving to the left at 0.500 meters per second and block A is moving to the right at 2.00 meters per second. Two blocks are equipped with ideal spring bumpers. The collision is head-on, so all motion before and after it is along a straight line. Questions are: letter A, find the maximum energy stored in the spring bumpers and the velocity of each block at that time. And letter B, find the velocity of each block just after they have moved apart. We're given the mass of each block. All right, for block A, it is 2.00 kilogram, while block B is 10.00 kilogram. And as shown in the figure, the velocity of block A before the collision, that's denoted by V sub 1, equals positive 2.00 meters per second. That means block A is moving to the right, all right? While block B has a velocity denoted by V sub 2 equal to negative 0.500 meter per second. So, block B is moving to the left. In other words, these two blocks will collide, all right? And our target variable for letter A is the maximum stored energy in the spring bumpers. That's denoted here by capital U, max. Also, we want to know what the velocity of the two blocks at this instant. All right. We denote the velocity of each block as u sub 1 and u sub 2. But during the impact, the two blocks will have a common velocity. All right. When the stored energy in the spring bumpers is maximum, all right, the two blocks will have a velocity that is common for both of them. So we also consider this velocity as the velocity of their center of mass, denoted by V sub cm. And for letter B, the other two variables are the velocity of the two blocks, B sub 1 prime and B sub 2 prime, for block A and block B respectively. This is just after the collision or separation. So in computing the maximum elastic potential energy of the bumper spring, denoted here by capital U max, all right, we need to first find the total kinetic energy of the system before the collision, and then deduct from it the kinetic energy of the center of mass of the system, denoted by Ke Cm. Alright, for the total kinetic energy before the collision, we just use the formula 1 half MAB1 squared plus 1 half MBB2 squared. And before we can find the kinetic energy of the center of mass of the system, we need to first find the velocity of the center of mass of the system denoted by B sub Cm using the formula MAV1 plus MBV2 all over the total mass MA plus MB. So, after which, we can already find the kinetic energy of the center of mass, the system, using the formula Ke of the center of mass equals 1/2 multiplied by the total mass MA plus MB and times the square of the velocity of the center of mass. And for question letter B, to compute for the final velocity of block A after the collision, right, as well as the final velocity of block B after the collision, we need two equations. The first one is what we use also in problem number 1, which is uh, B1 prime equals B2 minus B1 plus B2 prime. All right. This was taken from the formula for the coefficient of restitution. All right. And the other formula, of course, is based on the conservation of linear momentum. MAB1 plus MBV2 equals MAB1 prime plus MBB2 prime. Moving on with our computation, starting with the total kinetic energy of the system before the collision, all right, using this formula. That is, the total kinetic energy of the system before the collision equals 1/2 the mass of block A 2.00 kilogram multiplied by the square of its velocity before the collision 2.00 meter per second. So that's to be squared. Plus 1/2 the mass of block B 10.00 kilogram times the square of its velocity before the collision 0.500 meter per second. So when you do our math, we find the value of the total kinetic energy of the system before the collision equal to 5.25 joules in three significant figures. Next, we find the velocity of the two blocks, or the velocity of the center of mass, all right, of the system denoted by B sub Cm using this formula. Quantity MA times B1 plus MB times B2 all over the total mass MA plus MB. All right. If you recall, this is also the formula uh, in finding the common velocity of two objects after they collide, okay, in an what we call perfectly inelastic collision. All right. So we are using this formula because during the impact, when the stored energy in the bumper's spring is maximum, all right, we say that the two blocks, all right, are moving as one body or one system, all right. Uh, and earlier, we also consider this as the velocities that was asked, all right, in question letter A, all right, denoted earlier by uh, use of 1 and use of 2, all right. So, substituting the given data, B sub Cm is equal to 2.00 kilogram, that's the mass of block A, times um, its velocity before the collision, 2.00 meter per second, all right, plus that of block B, all right, whose mass is 10.00 kilogram, times its what we call velocity before the collision, 0.500 meter per second, then all over their total mass, which is 12 kilogram. Again, when we do our math, we get the value of V sub cm equal to negative 0.0833 meters per second in three significant figures. So we emphasize that this is our answer, or part of our answer to question letter A, right? That is, this is the velocity of each block during the impact when the energy stored in the spring bumpers, right, was considered maximum. Each block will have this final velocity equal to negative 0.0833 meters per second. Computing the kinetic energy of the center of mass of the system, all right, we have the formula 1/2 multiplied by quantity ma plus mb, okay, times the square of the velocity of the center of mass of the system, right? That is, Ka of the center of mass equals 1/2 times 12.00 kilogram, all right? That is the total mass of the two blocks, and then multiplied by the square of the velocity of the center of mass, negative 0.0833 meters per second. Doing our math, we get the kinetic energy of the center of mass of the system equal to 0.0416 joules, also in three significant figures. So we can now continue in our computation for the maximum elastic energy that is stored in the bumper's spring, denoted by capital U max. So we just deduct the total kinetic energy of the system before the collision minus the kinetic energy of the center of mass, Ka sub Cm. That is, capital U max equals 5.25 joules minus 0.0416 joules. So we get the value of the maximum potential energy stored in the bumper's spring equal to 5.21 joules, also in three significant figures. Computing the velocity of block A just after the collision or separation, we have V sub 1 prime equals V sub 2 minus V sub 1 plus V sub 2 prime, or that is V sub 1 prime equals negative 0.500 meters per second, right, minus 2.00 meters per second plus the unknown variable V sub 2 prime. So we can simplify this to negative 2.50 meters per second plus V sub 2 prime, right? So to find the variable V sub 2 prime, we calculate for the total momentum before the collision, right? That is, this is the total momentum before the collision, or the left side of our general equation here, right? That is, the mass of object or block A, 2.00 kilogram, multiplied by its velocity before the collision, 2.00 meters per second, plus the mass of block B, which is 10.00 kilogram, multiplied by its velocity before the collision, negative 0.500 meters per second. All right? So that is simplified to 4.00 kilogram meter per second minus 5.00 kilogram meter per second, or the total momentum before the collision, denoted by P sub t, equals negative 1.00 kilogram meter per second. Likewise, we also calculate for the total momentum after collision. That is labeled as Pt prime. So that is equal to the mass of block A, 2.06 kilogram, and its what you call velocity after the collision v1 prime, which is earlier expressed as negative 2.50 meter per second plus v sub 2 prime. All right? So that is what we multiply to the mass 2.00 kilogram, and then add to that the momentum of block B after the collision, 10.00 kilogram, that's the mass of block B, and of course times its velocity after the collision, v sub 2 prime. And simplifying, that becomes negative 5.00 kilogram meter per second plus 2.0 kilogram b2 prime plus 10.00 kilogram b2 prime. Combining these last two terms, we can further simplify the total momentum after the collision pt prime in terms of negative 5.00 kilogram meter per second plus 12.00 kilogram multiplied by b sub 2 prime. And equating the two total momenta before and after collision, all right, the total momentum before the collision was earlier determined as negative 1.00 kilogram meter per second. So we now equate that to the total momentum pt prime, that is negative 5.00 kilogram meter per second plus 12.00 kilogram times b2 prime. And solving for b2 prime, all right, or isolating b sub 2 prime, we have b sub 2 prime equals 4.00 kilogram meter per second divided by 12.06 kilogram, or that gives us the value of b2 prime equals positive 0.333 meters per second. All right, that is the velocity of block B after the collision in three significant figures. So going back to b sub 1 prime, all right, that is b sub 1 prime, which is equal to negative 2.50 meter per second plus b sub 2 prime, which is now determined as 0.333 meter per second. We finally get, all right, the final velocity, or velocity b sub 1 prime, this is for object A after the collision, equal to negative 2.17 meters per second in three significant figures as well. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.